Thrust, propellers. The propeller is a means of converting the power developed by an engine into propulsive force. A rotating propeller imparts a rearward motion to a mass of air. The reaction of the rearward motion is a forward force on the propeller blades. The basic shape of a propeller blade is that of an aerofoil. The propeller is driven either directly by the crankshaft of the engine or by a gearbox to reduce propeller RPM. Thrust is the propulsive force. Torque is the resistance to rotation or propeller load. In this diagram, the propeller is positioned for normal flight. Thrust is in the flight direction. There is a small task vector as a relative airflow is behind the chord line. The magnitude of thrust and torque depends on the size, shape, number of blades, blade angle, speed of propeller rotation, air density and forward speed. A lot of these things directly relate to the lift formula from principles of flight. Lift equals CL half rho V squared S. Naming of propellers. A tractor has the propeller on the front of the engine, which is most aircraft that we see. The pusher, though, has the propeller on the rear of the engine. In line, two propellers or more behind each other. Right-handed, when viewed from the pilot's cockpit viewpoint, the propeller will rotate clockwise, and left-handed from the pilot's cockpit viewpoint, the propeller will rotate anti-clockwise. Propeller terminology. Angle of advance, helix angle, is the angle between the relative airflow and the rotational velocity and relates to the true airspeed. Blade angle is the angle between the plane of rotation and the blade chord. Angle of attack is the angle between the relative airflow and the chord. Here's another image of propeller terminology where B is angle of attack, which is the angle between chord line and relative airflow. C is chord line to plane of rotation, blade angle, and D is relative airflow to the plane of rotation, angle of advance. The propeller blade. Each blade is an aerofoil. Thrust will be produced most efficiently at a particular angle of attack. Angle of attack for a propeller is defined as the angle between the chord line at a particular point, blade station, and the relative airflow. Blade angle equals angle of attack plus angle of advance. For a fixed pitch propeller, blade angle is fixed. So with no forward velocity, the angle of advance will be 0. So blade angle will be angle of attack. As forward velocity increases, the angle of advance increases, and for a fixed blade angle, the angle of attack must therefore decrease. The optimum angle of attack is 3 to 4 degrees. Geometric pitch. Geometric pitch is the distance that the propeller is expected to move forward in one revolution. Fixed pitch propellers are typically classified by their diameter, pitch and blade angle at 3/4 radius. Air is not solid and the propeller is subject to slip. Slip results in effective pitch. Geometric pitch is made up of effective pitch plus slip. Propeller forces. Centrifugal. There's a radial stress parallel to the blade axis, and also a force at 90 degrees to the blade axis, which twists the blade to a finer pitch. Thrust. Thrust bends the propeller forwards in the direction of flight. Torque. Torque bends the blades opposite to the direction of rotation. Air loads oppose the centrifugal twisting moment and coarsen blade pitch. Propeller blade angle of attack. The angle of attack will vary with operating conditions and with camber of the blade section. The rotational speed of the propeller blade section increases with distance from the root. Blade angle is the angle between the plane of rotation and the chord line of the propeller. To achieve a relatively constant angle of attack along the blade length, blade angle is decreased from blade root to tip. Increasing absorption of power. Absorption of power may be increased by increasing the following: blade angle, diameter, camber, chord, number of blades, or solidity. Solidity of the propeller is the ratio of propeller disc area covered by blades to total disc area. Swing on takeoff. Asymmetric blade effect, P factor. If the axis of rotation is inclined in relation to the horizontal path of the aircraft, the downgoing blade has a higher angle of attack and therefore produces more thrust. It also travels further per unit of time and produces more thrust. Torque reaction. This rolls the aircraft in the opposite direction to propeller rotation and is counteracted by wing washout on the wing that lifts. It causes the wheels on the opposite side to the downgoing propeller to take more weight and thus turn less, causing yaw. Slipstream effect. The slipstream rotates the same way as the propeller. On the downgoing side, more lift is generated on the fin. This may be counteracted by offsetting the fin or biasing the rudder. Gyroscopic effect. As the tail wheel leaves the ground, for a tail dragger, the nose will be pitching down. This torque is precessed by 90 degrees from the point of application in the direction of rotation. Variable pitch propellers. Primary controls. The engine throttle, which is the black levers, controls the engine power setting. The RPM control lever, which sets the required engine speed within the pitch range of the propeller. There's blue knobs on the end of it. The red levers are the mixture settings. Variable pitch propellers can change their pitch angle. The RPM control lever. The RPM control lever is connected to a control unit known as the constant speed unit that is mounted on and driven by the engine. The CSU acts as a governor and maintains the selected engine speed. As engine speed increases, propeller RPM increases as the propeller drive shaft turns faster. The increase in propeller RPM is sensed by the CSU, which moves the propeller blade to a coarser angle. This makes the engine work harder to turn it, thus reducing engine RPM. As engine speed decreases, propeller RPM decreases, as the propeller drive shaft turns slower. The decrease in propeller RPM is sensed by the CSU, which moves the propeller blade to a finer angle. This makes it easier for the engine to turn it, thus increasing engine RPM. Single acting constant speed. Oil pressure operates the pitch change cylinder to the fine pitch. Centrifugal force and a spring move the propeller to coarse pitch. In the double acting constant speed mechanism, oil pressure operates the pitch change cylinder both ways. Variable pitch positions. Extra fine, fully fine, ground fine. This is for easy starting. There's reduced drag. Pitch automatically increases to normal fine, i.e. more coarse, to increase airflow for engine cooling. Fine pitch stops automatically engage, which prevent the propeller from moving back to extra fine, and therefore preventing it going too fast. The constant speed range for normal operations, propeller speed is sensed and governed by the CSU. Feathering stops prevent the propeller moving into a fully coarse position. Feathered. This prevents windmilling, in other words, the propeller being driven by the wind, in the case of a failed engine. Braking. The propeller is moved past the extra fine position so that it produces reverse thrust. Windmilling propeller. The windmilling propeller is positioned as if for normal flight, but thrust is opposed to flight direction and there is a huge TAS vector as relative airflow is ahead of the chord line. Feathering. Feathering is moving the propeller to a fully coursed position. To achieve this, the RPM lever is usually moved through a gate in the quadrant. This raises the governor valve fully, allowing oil to drain out. The blades turn to the fully coursed position under the action of the counterweights and spring. The feathered propeller in the diagram is pitched at nearly 90 degrees to the plane of rotation. This reduces drag. Unfeathering. Unfeathering removes the propeller from the feathered position. A separate source of oil under pressure is required. On light aircraft, this may be via an accumulator, which is charged during flight. To achieve this, the RPM control lever is moved into the constant speed range. An auto-feathering button may be pressed, releasing oil from the accumulator to the propeller. The blades begin to unfeather, and as soon as the propeller starts to windmill, the normal oil supply takes over. Shutdown. On shutdown, oil pressure is gradually relieved by leakage through the CSU, which would send the propellers under spring pressure to a feathered state. Propellers need to be prevented from feathering during shutdown, since starting from a feathered state would produce extreme loads on the engine. To stop the springs moving the propeller to the feathered state, a centrifugal latch is fitted to prevent forward movement of the propeller piston. Turboprops. A turbo propeller is the propeller which is driven by a gas turbine engine. The power control lever is normally connected to a fuel control unit and a propeller control unit. Automatic feathering is initiated by a torque switch, which is operational when the power levers are set above idle. If engine torque falls below a critical value, the torque switch closes and completes the circuit to a feathering pump and a solenoid valve in the propeller control unit. The solenoid directs oil to the valve lift position, which lifts the governor valve, opening oil ports from the feathering pump to the front of the pitch change piston. Beta control for ground operations. Blade angle control is used for ground operations. During flight, the power levers operate in a gated quadrant, which stops the levers from being closed past flight idle. The CSU governor operates normally. On the ground, the power levers control propeller pitch to vary power at positive and negative blade angles at constant propeller speed. The CSU governor is overridden. Here's a reminder about fixed pitch propellers. The blade angle of the propeller is fixed. The relative airflow is governed by the true airspeed of the aircraft and propeller RPM. An increase in TAS reduces angle of attack. An increase in RPM increases angle of attack. Angle of attack may be reduced to 0 at high forward speeds, low RPM situations, for example in a power-off dive. However, at low forward speed, high RPM, for example the climb, blade stall may occur. For a fixed pitch propeller, there is only one combination of TAS and RPM for maximum efficiency. When a fixed pitch propeller is driven by a piston engine, RPM depends on power set, i.e. throttle position, and true airspeed. Variable pitch, constant speed propellers allow the adjustment of RPM for changing TAS and flight conditions. Separate power levers, throttle, and RPM control levers are provided so that it is possible to vary one whilst leaving the other constant. A selected RPM can be maintained and braking feathering facilities may be incorporated. A constant speed unit or propeller control unit automatically varies blade angle and therefore angle of attack, so that the selected RPM can be maintained even though speed and engine manifold pressure may themselves change. Here's a diagram of the different blade angles a variable pitch propeller can achieve. At 0 degrees, the propeller is in line with the plane of rotation. If it moves slightly forwards, it would reach a point called ground fine, and further than that, flight fine. Flight fine is where the alpha range commences. It's a constant speed range up to flight course. Beyond that, the propeller can achieve a blade angle of up to 90 degrees in the feathered state. In the beta range, the propeller is now behind the plane of rotation as much as 20 degrees and can provide reverse thrust or braking. The centrifugal latch prevents blades from moving to the feather position when the aircraft is on the ground and the engine is switched off, due to a leakage of oil through the CSU relieving pressure in the pitch change cylinder. The centrifugal force disengages the latch at all speeds above ground idle. On start-up, oil pressure builds up to move the propeller blades to the fully fine position. Counterweights on a single-acting variable pitch propeller try to move the blades to coarse pitch. The centrifugal twisting moment tries to move the blades to fine pitch. The CSU oil pump boosts the oil pressure from the engine lubricating system sufficiently for the operation of the propeller pitch change mechanism. To feather a single-acting variable pitch propeller, RPM lever is moved fully aft to the feather position. Oil drains from the propeller and blades turn to the feathered state under the action of the propeller counterweights and spring. To unfeather a single-acting propeller, a separate source of oil under pressure is required. On light aircraft, this is provided by an accumulator which is charged during normal flight. The pilot's RPM lever is moved into the constant speed range, which releases oil from the accumulator, allowing it to flow to the propeller. Once the propeller starts to windmill, normal oil supply completes the operation. In the on-speed condition, spring force is balanced by flyweight force, and oil ducts to or from the pitch change cylinder are blocked off, i.e. a hydraulic lock is formed. Constant RPM is maintained. In the overspeed condition, the flyweights move outwards and raise the governor valve against spring pressure. Oil drains from the pitch change cylinder to increase pitch. In the underspeed condition, the flyweights move inwards and the governor valve is pushed down by spring pressure. High pressure oil enters the pitch change cylinder to decrease pitch. Double acting propellers. Hydraulic pressure is used to operate the pitch change in both directions. No springs or counterweights are required. To feather, the RPM lever is placed in the feather position. The feather button in the cockpit must be pushed. This operates an electric pump which draws its supply from the emergency stack pipe in the oil tank. A pressure operated cutoff switch releases the feathering button as the feather oil system pressure rises to a specified value. To unfeather, the RPM lever is placed to max RPM, the ignition switch is placed on, and feather button is pressed. The CSU goes to an underspeed condition and oil is ducted to the decreased pitch line. Autofeather. This enables very fast response to engine failure, especially in large engines turboprops where windmilling drag is high. A negative torque system senses the difference between power selected and power actually achieved. If engine failure occurs, an increased pitch solenoid is energized and oil is ducted to the increased pitch lines. System operation may depend on the throttle lever position, such that autofeather is active at the high end of the power range rather than the low end. Turbo propellers. The power control lever is a single lever connected to both the propeller control unit and the fuel control unit. RPM and fuel flow are altered together. Manual feathering. The power control unit and engine high pressure cock are interconnected. When the HP cock is closed, the propeller control unit governor valve is lifted up and oil pressure turns blades to a feathered position. Automatic feathering. This is achieved by a torque switch when the engine torque falls below a specified value and there is a high power selection. A valve lift solenoid directs oil to the valve lift position, which lifts the governor valve and feathers the propeller. Beta range operation. Beta range is used only on the ground, although some aircraft can actually use it in the air. It's selected by pulling power lever into the ground range. The flight fine pitch stop is removed provided there is weight on the wheels. With the RPM lever set at maximum RPM, the beta range is controlled by moving the power lever rearwards. Pitch angle is made more negative as the power is increased. Blade angle is directly controlled in the beta range. Allied signal TPE 331. The cockpit controls. The power lever has reverse, ground idle, flight idle and maximum settings. The condition lever has cut-off, low RPM and high RPM. The power lever is connected to both propeller pitch control and the fuel control unit. In flight, the power lever operates the fuel control unit. In beta range, the power lever bypasses the propeller governor and directly controls blade angle through the propeller pitch control unit. The condition lever is connected to a primary and underspeed governor. In flight, the condition lever sets the RPM on the propeller governor, allowing the governor to vary blade angle so that engine RPM remains constant. In the beta range, the condition lever adjusts the underspeed governor by varying fuel flow to maintain fixed RPM in spite of blade angle changes caused by power lever adjustments. The Pratt Whitney PT6, as used on the King Air Twin Otter PC-12 and Sikorsky 76. The cockpit controls have a power lever, propeller control lever and a condition lever. In flight, the power lever controls the engine output power by adjusting the fuel control unit. In the beta range, the power lever controls the fuel control unit and propeller blade angle. The propeller control lever is connected to the propeller governor. Full aft movement will feather the propeller. The condition lever sets the gas generator's low, ground and high flight idle RPM.